In this series of videos, we're going to talk as succinctly and briefly as reasonably possible about finding the zeros, or as they're sometimes called, the roots of polynomials. And by that we mean both real and complex zeros. You have to understand, though, if you look in a typical textbook from which this material would be drawn, you know, a pre-calculus text or a college algebra text or some equivalent, typically this spans several sections from the text. So it's not something that can be covered in a single 10-minute video or explained in a meaningful way, a useful way in 25 words or less. It takes a little bit of time to cover this reasonably. And so we'll try to be as efficient as we can, but you have to understand there's quite a bit here. What do we expect you to know? Well, people come into our class and, you know, I never know their backgrounds. In some cases, it may have been many years since they took the class which comes before this. So we try to do our best to give a little bit of just-in-time remediation. In this case, I think it's probably safe to assume that most people know what a polynomial is, but it doesn't hurt rather to emphasize the obvious, at least in my experience. And the vocabulary that's associated with polynomials becomes particularly important when you start to talk about finding roots and finding zeros. So, good working definition is on the screen in front of you right now. You could look it up in your text to see what they say about it, but what I would prefer to say is that a polynomial is a finite sum of power functions with real coefficients, at least in our class, and non-negative integer exponents. And again, you can see several examples of polynomials on the screen in front of you right there. Regarding the vocabulary, let's take one of these polynomials as a particular example. Look at the sixth degree polynomial that's visible there. H of x is 4x to the sixth power minus 16x to the fifth plus 12x to the fourth, and so on. If you're looking at that and wondering, is the fact that the highest power present is 6 and the polynomial is sixth degree, is that connected in some fashion? It is. When you have a univariate polynomial, that is a polynomial in one variable, the highest power present is the degree of the polynomial. Why would you want to know that? Well, you know, the degree tells you a few things. It tells you about the end behavior, if you know that. And it also tells you, when you're hunting for zeros, basically how many you're going to be looking for. So it's good to know about the degree. Now, if you're wondering what's a power function, well, you can look at the components of that polynomial there, h of x, and you can see several examples of power functions. For example, the leading term is 4x to the sixth power, and that's a power function. And the next term, negative 16x to the fifth, that's a power function. And the next term, 12x to the fourth, that's another power function, and so on. Now, the numbers that you see written next to the variable expressions, those are the coefficients. So again, looking at h of x, the leading coefficient would be 4, because that's the number attached to the dominant term, x to the sixth power, right? And then the coefficient of the x to the fifth term would be negative 16, and the coefficient of the x to the fourth term would be positive 12, and so on and so on. The only other term that is significant that has its own designation is the last term of the polynomial. In the case of h of x, it's 20, positive 20, and that's known as the constant term. You'll see that when you graph those polynomials, that constant term is the y-intercept. And that's going to be something that plays a role in finding zeros, and so that's why we are emphasizing that. It also is important when we're doing polynomial division, as you'll see. Now, in terms of big picture knowledge, it's important to realize that polynomials can have two kinds of zeros. They can have real zeros, which would include rational and irrational, and they can have complex zeros. You can find examples of polynomials that have exclusively real zeros, and you can find examples of polynomials that have exclusively complex zeros, and you can find examples of polynomials that have a blend of both kinds. So you never know what you're going to get, and when you're looking at a polynomial in expanded form, it's very hard to know exactly what kind of zeros it has unless you're willing to do some analysis. Now, when it comes to the complex zeros, it's going to be important to keep in mind that if you have a polynomial with real coefficients, which the ones in our class are going to have, the complex zeros necessarily come in what we call conjugate pairs. They always come 2 by 2, in other words. And we'll have more to say about conjugates down the road, but it's important to know that when you're considering how many zeros am I hunting for here, you have to recognize that if there are complex zeros, they're always going to be an even number of complex zeros. So 2 or 4 or 6 or however many, but it's always going to be an even number. The real zeros, you can have an odd or even number depending on whatever kind of polynomial you have, but the complex zeros, you're always going to have an even number. Now, in terms of tools that we use for finding these zeros, we do assume a certain amount of background knowledge. So, for example, we expect that you know what the factor theorem is, and what the remainder theorem is, and what the rational zeros theorem is. And if you don't, you can look them up in your text. You'll find them there. We also are requiring a graphing calculator for this course, and so that's something we're going to be making use of. We use it to be more efficient when it comes to finding roots, as you'll see. We also are going to do polynomial division, and primarily it's going to be synthetic division. That's the most efficient, but sometimes you got to do long division. And so that's kind of one of those things where, we're going to show you examples of it, but we really don't have time in this series to do an in-depth review of that. And so that would be one of those things where I would say, YouTube is your friend. If it's been a while since you've done polynomial division, or if you never have done polynomial division, or if it's been a while since you've done quadratic formula, or you've never done quadratic formula, those are things that we're going to use in this class, but we assume when people come in that they know how to do those things. That's part of the prerequisites of the material, the class that comes before, right? So I will not do a lot of review of those things in this series, and if you need some review or you need some kind of a refresher, you can go on YouTube and search, and you should have more videos than you could ever watch. There's really going to be a large number that you'll find, and so it's very easy to get that review from there. Now, if you're paging through your text and you're looking at the various theorems that can be found in typical coverage of this material, you might notice that there's a lot more than the factor theorem and the remainder theorem and the rational zeros theorem. And so you might wonder to yourself, do I need to worry about those other theorems like Descartes' rule of signs or boundaries on roots or other things like that? And I would say, well, actually, those theorems were much more important in the time before graphing calculators and graphing technology became readily available. And so we don't really mention those because we're not really using them in our particular approach. You can use them if you want, but it's sort of not as efficient as what we're proposing here. Now, I'm not saying that you shouldn't know those theorems, but just that in this particular video series, I'm not going to be using those much. The ones that I'm going to use are the factor theorem, the remainder theorem, and the rational zeros theorem. Now, regarding the rational zeros theorem, this is a good example of how to phrase that particular theorem. You can probably find an equivalent version in your text. What this theorem is saying, in effect, is that if you have a polynomial and it has rational zeros, so in other words, it's not saying that all polynomials have to have rational zeros. It's saying that if it does have rational zeros, those are going to come in a certain form. And as you can see here, the numerator of those rational zeros, which is represented here, the form of it is p over q. So those rational zeros are going to be of the form p over q, and the numerator of those rational zeros is going to come from factors of the constant term. In a similar fashion, the denominator of those rational zeros is going to come from factors of the leading coefficient. And so this is one of those theorems which, we kind of expect you to know because it can be helpful to know, but it's not really one of our go-to type tools in our search for zeros. However, we do encounter many questions about it, and many people find it confusing, which is why we're including it in this video here. So let's take a look at some examples of the rational zeros theorem in action and see what we can see. Hopefully you can see the iPad in front of you on the screen there. And this first example is a polynomial, and they're helping us out. They're giving us the polynomial and the graph. If they had just given us the polynomial, we would probably be using our calculator to get the graph, because having the graph is very helpful, as you'll see. So the instructions here are saying to use the rational zeros theorem to find all possible rational zeros of the given polynomial. Then use the graph to discern which, if any, are actual rational zeros of the polynomial. Now, one thing to notice here about this graph, you'll notice if you look carefully that it appears that we have a fractional root. Let me get a good color here to indicate that. It's right there. And notice also that the scale on the axes is different. So on the y-axis, a single hash mark represents a distance of 1 unit, but on the x-axis, a hash mark represents a distance of a half unit. So important to catch that little detail. It's very, very easy to overlook that. But reading fractional values like that can be tricky because they all look like 1/2 or 2/5 or something like that. It's very, very difficult to read those with any real accuracy. But in this case, it's permissible because it's part of the instructions. They're telling us, look at that 0 right there and see if it's one of the ones that the rational zeros theorem is going to cough up. Now, as far as this polynomial is concerned, the constant term you can see is -2. It does own the sign in a manner of speaking. I mean, it is -2, but we don't really care about the sign. We just care about the 2, more or less. And the leading coefficient in this case, since the dominant term is a 3rd degree term, would be a sub 3. And it is positive 3. And so as far as what the rational zeros theorem is saying, it's going to give us a list of candidate zeros. RZT, of course, being rational zeros theorem. And so what I recommend when you're making a list of these is that you want to try to be as systematic as possible. It's really easy to lose your way if you're not being systematic. So what I'm saying is something like the following. Take a look at the constant term there. What are the factors? Well, you can have positive and -1 and positive and -2. And when we ask you what the factors are, we're asking in effect, what numbers would you multiply to what numbers would you multiply to make 2? And so it's a nice short list, happily. As far as 3, again, it's a nice short list. It's plus or minus 1 and plus or minus 3. And so when you start to make your list of candidate zeros, you pick a particular value of p, and you work through all of the possible combinations of that. So in other words, we're saying that P is going to come from here. And Q is going to come from the factors of the leading coefficient 3, right? And so here's what I'm saying. So we'll start with 1. And so we're going to have plus or minus 1 and plus or minus 1 over 1, plus or minus 1 over 3, because the other value of Q would be 3, you understand? And then the next value of P would be plus or minus 2, so we'll have plus or minus 2 over 1, and then plus or minus 2 over 3. Now when you make these lists, oftentimes there's a little bit of tidying up that you would need to do before you type the answer into your learning management system. There may be redundancy, for example. You might have a particular value that would pop up several times. So you don't have to type it in several times or write it several times. You're gonna put the clean version of your answer into your LMS, and so that would include reducing certain fractions, for example, if they're reducible. So in terms of my answer here, what I would be typing into my LMS, it would be plus or minus 1, plus or minus 2, right? Because 1 over 1 and 2 over 1, those both reduce. And then plus or minus 1/3 and plus or minus 2/3. Now, the next bit of the instructions are saying to go back to the graph now and try to identify which of those candidate zeros are actual zeros. And what you're supposed to notice here is that, when you list all of the candidate zeros using the rational zeros theorem, you may have what is a very long list. And typically very few of those candidates are actually going to be zeros, right? So the rational zeros theorem doesn't just cough up the zeros. It just gives you potential zeros, and then you have to work some additionally to figure out, well, what's what. So in this case, the actual zeros can be seen here. We have a 0 there, and that looks to be at -1. Would you agree? Because on the x-axis, recall, 2 hash marks are 1 unit, right? And then we have another one on the positive side, and my guess is that that is positive 2/3. Now, you might be wondering, is there some way that we could verify that that's the case? And I would say, well, yeah, actually there is. Let me show you. We require a graphing calculator for our class, and so probably the best way to check validity of zeros would be to have the graphing calculator check them for you. So if you wanted to key in that particular polynomial here, the polynomial is as follows. It's 3x cubed plus 4x squared minus x minus 2. And when you graph it, I don't know what an ideal window size is off the top of my head, but I would probably start with what I would call a standard zoom, which means you would go zoom, and then you see number 6 right there. It says Z standard. That stands for zoom standard, and so that's a good one to use here. It basically gives you a window that goes from -10 to 10 on both axes, and that's a good starting place. And I would say that that's a reasonable picture. It kind of looks like the graph that we saw in the text, or on the iPad in this case. And we can then verify the zeros as follows. So you can go to second trace, and you can put in a value. And so in this case, the first one we'd want to put in would be -1. Would you agree? And so you can see that it spits out y equals 0 right there, and that confirms that, yep, that is indeed a 0. It's a real 0 of that polynomial. And then the other one we were proposing was 2/3. And so we can put in 2 divided by 3. And again, you can see that it spits out 0. And so that confirms that both of those are actual zeros of that polynomial. Let's look at another example here. If you want to make sure that you're tracking with us, you could pause this video and you could try this problem for yourself. The instructions are the same. Basically, they want you to list all of the rational zero candidates, and then they want you to use the graph to indicate which of those are actual zeros. Obviously, I'm not going to leave a long pause in the middle of the recording here. I'm going to cut to the chase, but if you want to work it yourself, you can just pause the video and do it on your own paper. So, polynomial has a constant term of +1 and a leading term of +4. And so, if we're writing down what's what, the factors of the constant term, nice short list, positive and -1. The leading term has a coefficient of 4, and the factors of that, positive and -1, positive and -2, positive and -4. So what are the candidates for rational zeros here? Well, positive and -1 over 1, positive and -1 over 2, positive and -1 over 4. And by the way, I didn't mention this previously, but it's worth to mention. Notice how many zeros we're actually proposing here. So we have 3 numbers listed, but they're positive and negative versions of each one. So in fact, we're proposing a total of 6 candidate zeros here. Likewise, for the example that we did before, we were proposing a total of 8 candidate zeros. And of those 8, only 2 ended up being actual zeros. And likewise, when you look at this example here, you can see that only 2 are going to be actual zeros. So in terms of actual zeros, Now notice this graph has the same type of scaling as the prior example. So 1 hash mark on the y-axis is equal to 1 unit, but on the x-axis, 2 hash marks is equal to 1 unit. So that one right there is very clearly x is 1. And that one right there, it's a fractional root, obviously, but it looks to be halfway between 0 and 1/2. And so that seems to me that it would be 1/4. And I'm thinking that that is our root right there. Now, of course, we can verify that. Let's put down our answer before I forget here. So it looks like it's going to be x is 1/4 and x is positive 1. And so if you're typing that into your learning management system, you'd probably also want to clean that up there, because it's going to be positive or negative 1, and then positive or negative 1/2, and then positive or negative 1/4, right? And of course, we can resort to using the calculator to verify that those candidate roots are in fact roots. So let's key that in and clear this out. Our polynomial is given. It's 4x to the 4th minus x cubed minus 4x. Whoops. Got to make sure to get out of the exponent there. Minus 4x plus 1. And let's just graph it and see what we have here. That's a reasonable view. It looks about correct. And then in order to check those values, we can go to second trace, put in a value. We'll put in 1/4 first. And you can see that the calculator spits out a 0 right there. That's a good sign. And then we can also put in x is 1. And again, you can see that it spits out a 0. And so those are both actual roots. Hope that this has been helpful. Please stay tuned for the next video in the series.